All right, so talking about waves, and our example is very wordy, but here we go. So Biff figures he should have exactly 12 hours of each, and it's each okay, let me try this again. 12 hours of daylight each on both the spring and autumn equinoxes, which happen approximately March 21st and September 21st, respectively. The summer solstice, which is June 21st, he had 17 hours of daylight. In other words, 15 hours extra that he didn't have on the equinox. And on winter solstice, which happens around December 21st, he expects to have 7 hours of daylight. In other words, 5 hours less than he had on the equinox. Write an equation for a sine wave that would give Biff the approximate number of hours of daylight on the xth day of the year. So if we wanted to find the number of hours on the 31st of January, we're going to let x equal 1 be January 1st. So January 31st would be day 31. So we could plug in 31 for x and calculate the amount of daylight on January 31st. If we wanted February 28th, well, we'd have to take the 31 days in January plus the 28 days in February. So that would be 59. We'd plug 59 in for x. And I will show you on the next page some of the values for x for the special days of the year. Because it's going to be necessary for this problem as we move forward. So in order to write our equation, just a reminder from yesterday, our equation is going to be the amplitude times sine of the frequency times the quantity x minus the phase shift plus the bias. And these values, amplitude, frequency, phase shift, bias, the easiest two to find are the amplitude and the bias. So the amplitude is always going to be the maximum minus the minimum divided by 2. In this case, our maximum hours of daylight occur at the summer solstice, easy for me to say, and our minimum occurs at the winter solstice. So we're going to take 17 minus 7 and divide by 2. The bias will be basically the minimum value. No, I'm sorry. Will be the difference from our middle value, which is the amount of daylight on the equinox, and 0. So in this case, our bias is 12. So we can start our equation. I'm gonna put it a little bit lower because we still have some things to calculate. But amplitude is 5. Sine. We'll fill this in a minute. Plus the bias. All right, so the phase shift is going to be where we hit the value for our bias. And really for the first time. So March 21st would be the value of X for our phase shift. And so now I'm going to flip to the next page and give you a couple of key X values for dates. So March 21st is X equals 80. That's going to be our phase shift. So that's the spring equinox. Summer solstice is where X equals 172. The autumn equinox is X equals 264, and the winter solstice is X equals 355. And then the end of the year, if you wanted, this is assuming, I guess I should have maybe included this. January 1st is X equals 1. December 31st is X equals 365. We'll assume we are not in a leap year. So our phase shift is going to be 80. And the frequency is always going to be 2 pi divided by how long it takes us to go through one sine curve. In this case, it takes us a whole year. So it's 365 days. This equation then will approximate the number of hours of daylight for any day of the year. And you can, test it, find out. So what a couple of things, if you do test it on your calculator, go to my calculator, here we go. Try that again. All right. You want to make sure your mode is set to radians and not degrees, because of the fact that we're saying 2 pi as part of our frequency. So radians are going to be important. And if we go in here, 5 sine 2 pi divided by 365 times x minus 80 plus 12. And I have to make sure that I put the plus 12 so it's not in the sign. So that's why I have 2 parentheses there. And we can actually see what this looks like on the graph. So I'm going to change my window, though, to do that. I know x is going to be a full year, so it goes 0 to 365. And let's go by, I don't know, 10. 10 will be fine. My daylight goes from 7 to 17, so I'm going to go a little bit less than that, maybe 4 to 20. And I'll just go by ones, that's fine. And so if I graph it, I should get that sine curve if I did it right. All right, what did I not do right? Five sine 2 pi over 365 x minus plus 12. Oh, let's see. I'm going to draw one other line in here because yeah, so because of that phase shift, if I start where the red line and the blue line intersect, we go down, up, down, and then come back up. It just, because it doesn't have that full normal look to it, having that line in there actually might be helpful. And then if we wanted to, like I said, we could check to make sure our function is right. And these dates, we should know the number of hours of daylight. So if I plugged in x equals 264, we should get 12 as our answer. So if we go to our calculator, and we could look at a table. 264. Oh, okay, let's try that again. I know what happened. Let's go there. There we go. So, you know, it's an estimate. So we're not, I mean, it's not going to give us the exact value, but pretty close to 12 hours at day 264. All right. And that's the example. So I know for the homework, I believe the first question deals with something very similar. It's light in Juneau, Alaska. And then the second question is the amount of daylight in Sydney, Australia. And there's some good information on how you can do that. One of the keys will be the X value for the specific days here. to help you with the phase shift. And then the other ones deal with a Ferris wheel and some population of animals in a area of woods. So if you have questions on it, feel free to ask, and then I'll see you tomorrow.